So let's continue. Or I feel like I probably say that every video. So let's continue our discussion of pressure. We looked last time at pressure change in a column of fluid, as you can see. Now let's apply this a little bit in a few different ways. Right? So one is, um, so you can see a diagram like this in your book. At least in our book. I'm sure if you're using a different book, you'll find something very similar. Notice there's kind of it's kind of small, but notice down here there's an equation that says PA PA is equal to PB is equal to PC is equal to PD is equal to PE. What they're saying is at all of these points, because all of these points are at the same height, H. They're all saying they're all at point H. And so they're all at the same pressure. And that pressure would be the atmospheric pressure plus the density of the fluid times gravity times H. Now, there's this symbol up here, and it's kind of small. I'm going to draw a little bit bigger. So you have this triangle with some lines underneath it. That symbol means that that is open to the atmosphere, right? That symbol says open to the atmosphere, or P is equal to 1 atmosphere. Right, that's what that symbol is saying right there. So you can see the smaller version of it right here, and that's what they're telling you. And so what they're telling you is that the pressure at any point down here is equal to the initial atmospheric pressure plus the change in pressure based on the column of fluid to get down there, right? So what they're doing there is they're saying, well, let's switch to the document camera here. Right? If I stop share. Right, so we've got this situation where they're saying, hey, look, there's this fluid, and if we say that this is H, and this is open to the atmosphere up here, and we want to know what is the pressure at point A, right? Well, you've got a column of fluid here, so we're going to apply our fundamental equation for pressure change in a column of fluid, that is delta P is equal to rho G negative delta Z, Z1 minus Z2, right? And so what's given to us here, so if this is an example problem for us here, so what's given to us is if let's say I call this point 1, and we'll call this down here point 2, what I know then is let's say it's just density is equal to the density of liquid water. Let's just say it's a lake. All right, let's say that's given to us. Let's say they've given to me that basically the difference between Z1 and Z2 is this H value, right? And we know that P1 is equal to 1 atmosphere. Right? And so again, I know a difference in z's is to be the h value. What you want to do when you're working on these problems is we need to establish what are these z values, because I know the difference is h. Okay, well, what are the individual z values? Well, a simple thing you can do is set one of them equal to 0. And what I normally do is I pick a point that everything can be measured relative to easily, which either one of these is just fine in this case. But what I'm going to do is I'm going to say, well, let's say that Z1, let's just call that 0. That's the surface. We'll call that Z1 as 0. So we'll say that's given to me. And so if I'm calling this 0, everything below it is going to be negative, and anything above it would be positive because, again, we're using this form where z is referring to elevation. So if I say at the surface of the pond here, the lake or whatever it is if that elevation is 0, that means down here at Z2, it's below the 0 point, so it is at minus h. Now, there's nothing saying I couldn't say this is 0. I could call this 0, and this would be positive h. And mathematically, I'll get the same thing here. So if I'm saying Z1 is 0, that means I'm saying that Z2 is h distance below that, or minus h. Right? And so P is 1 atmosphere, or you could just say it's P atmosphere. Okay, and so we're going to say P2, which we're going to call PA, then is equal to uh, P1 plus rho G. And this is going to be, I'm going to plug in for Z1, I'm going to plug in 0. And for Z2, I'm going to plug in, we're going to minus Z2, and I'm going to plug in minus H here. So P2 is going to equal P1 plus rho GH, which is going to be, we're going to say that means PA, P2 and PA are the same thing. So PA is going to equal P1, which is the atmosphere. So we can either say 1 atmosphere or P atmosphere plus rho GH, which is what we have back over here on this slide. And that's what they're showing to us here. They're saying pressure at this point, and because it's the same elevation as the pressure at this point, is the pressure at this point, and they're all equal to this, the atmospheric plus pressure plus rho GH. And that's how we get there mathematically. Notice they're saying down here, pH is not PI. This point down here that's under a block of mercury is not the same as the um, pressure at this point. That's all water between here and there, right? So now I could find the pressure here, but that means I'm going to need to know how tall this column of mercury is. And I would need to know how much pressure, like how tall is this column of water from here to here. So basically, if I draw that in there, right, I would need to know, I've got, I would need to know another H here. We'll call this H2. And I would need to know this H3. Because what would happen is I would need to figure out, I've found the pressure here. That's this formula here. Then I would need to find the pressure here based on the pressure change from here to, you can't see that. I know the pressure here. I would need to find the pressure change from here to here based on this height. And I would need to find the pressure change from here to here based on this height and the density of mercury. Right? So it's doable, but I would need to stack like 3 of those equations that we just wrote. I'd need to stack 3 of those equations together, one for each of the 2 columns of water, and then a third one for the column of mercury. Easy enough to do, and we'll look at problems kind of similar to that. Okay. Now, there's a concept of Pascal's law. Again, quotes here without a source. That means it's a direct quote from your text, unless I give you another source, which I'll specify. But in this case, I haven't. That's from the Changle and Bowles text. The pressure applied to a confined fluid increases the pressure throughout by the same amount. So what that means is this is basically the concept of a hydraulic system or like a bottle jack, for example. So let's say that I've got here, I apply a certain amount of force over a small area, right? So that force is equal to pressure times area. And then if I apply that to a fluid confined in a space, that means that's going to cause an increase in pressure here at point 1, and it's going to cause the same increase in the pressure throughout that fluid, and it's going to end up manifesting over here at point 2. So what that means is if 1 and 2 are essentially at the same height, so I don't have a pressure change between the two, that the pressure here at point 1 is going to be the pressure at point 2. So by applying, and so if I write that out over here, P1 is equal to P2. Well, and each of those pressures is force per unit area, so that means F1 divided by A1 is equal to F2 over A2, which means if I want F2, which is what I'm after, F2 is going to equal, I'm going to put the ratio of areas here, that's going to be A2 over A1 divided by force applied at 1. And so what that means is that if I apply a small amount of force at point 1, it gets multiplied by a larger area divided by a smaller area. So this quantity here, it becomes a multiplier. So I can apply a small amount of force at point 1 multiplied by this larger quantity generates a larger force at point two. And that's essentially the idea behind a bottle jack. If you look at how that works, you've got this tiny little piston that you're pushing pressure on. A lot of times that's on probably like a hinge, right? So you got like some kind of a hinge that rotates about some point here. And what you can do then is you can apply an even smaller amount of force out here. And because of the torque, that generates a larger amount of force right here. Right? And then using that larger amount of force there gets applied over a very small area, and that generates a much, much larger force at this end over here. Right? So we don't have to understand too much about the mechanics of the machinery here. If you've had statics, you know a little bit about the moment of the force that we would generate there, and torque and whatnot, but that's not required for us. But it's just a neat little concept. We don't have to spend too long on it. It's worth mentioning. They mention it in the text. It's a neat application of pressure, but we don't really have to do much with that. Now, what we do need to work with is this idea of a manometer. So a manometer is a device that uses the phenomena of a pressure change in a column of fluid to measure pressure, right? So let's say that I've got some sort of gas contained in some sort of a tank or a vessel. And then I've got some sort of a liquid in this tube. We call a manometer tube, a U-tube shaped manometer. All right, so we have some sort of a fluid, and let's say we open this end up to the atmosphere. All right, so that triangle symbol we talked about earlier. And this fluid then has a height in its column H. And then, so what we can do then is we can basically say, well, the pressure of the gas minus the pressure of the atmosphere is going to equal the density of the fluid times gravity times the height of this column. All right, it's only because we're saying point one is open to the atmosphere and point two is basically the pressure of the gas. But this allows us to figure out the pressure of the gas. And then notice that if I wanted to know the pressure of the gas gauge, which is equal to the pressure of the gas minus the pressure of the atmosphere, well, that's just equal to rho g h. Now, keep in mind, this is a very simplified equation right here, right? This, you'll find if we ask Google, hey, what's the manometer equation? It'll say, well, the pressure is equal to rho gh. Well, that's only true if one end of the manometer is open to the atmosphere. You've got a single manometer fluid and it's at this height h. This is a very oversimplified equation for a very specific scenario. How often are you going to have this very specific scenario? I don't know. Maybe you do, maybe you don't. Just be aware of that. But that's for this particular setup, that's how we would set it up. Okay, how are we on time? Not too bad. All right. And so I've got an example. We'll probably work at the beginning of the next problem, but I do want to take just a minute or two and look at this video might go a little bit long, but I want to at least point to the other terms for anybody joining us that doesn't have our text. You can see the terms that I'm saying, hey, these are the terms I said last lecture are important, but we're not going to have time probably to cover them here. So important thing is problem solving. You guys are going to hear me throughout the semester hammer on how do we solve problems. For me, that's really our goal in a fundamental engineering course is we're going to learn thermodynamics, but I'm really trying to teach you how to solve problems, which means what am I looking for, right? What is it that I'm looking for? What do I know? So what does this thing look like and what is known? So what am I looking for? What's known? What tools do I have? What laws, equations, relationships can I use? Do I have enough information to solve, right? That's the calculations. Can I actually solve it? If I can't solve it, okay, what is unknown that I need to solve for? And we come back up here and now that becomes my new unknown. And then we say, okay, well, what do I know about that thing I'm trying to find now? Well, what tools, laws, and relationships can I use to find it? Write out another equation or find some additional unknowns. Do I have as many equations as I have unknowns? This becomes a loop, right? Right? It becomes a loop at some point, and if it's not solvable, you end up going back to the top. That's my alarm. I'm at 15 minutes. Like I said, this video is going to go a bit long. Um, but this is normally kind of the stuff that I don't have time in a regular class to talk too much about. So I'm going to go quickly through it here. But again, I am not minimizing this at all. This is really kind of the bread and butter. This is what we're trying to do in a course at this level is learn how to problem solve. So we'll hammer on this all semester long. So these are the terms, time allowing. So I'm going to go very quickly here. Please feel free to pause the video so you see what I've got here if you don't have the Chengle and Bowles textbook. If you got the Chengle and Bowles textbook and you've read chapter 1, you've seen all this stuff. Okay. I'm going to go quickly, very quickly here. This is normally not stuff I have time to do in class. State of a system just simply means we know all the properties for a system. So we've talked about pressure, volume, and temperature being the 3 properties we can measure. But if I know the state of the system, that means I've got some kind of model. It will also let me find the internal energy and the entropy. These are things I'll need to solve the first and second laws of thermodynamics. Again, going quick, so if you need to pause, pause. I'm going to keep moving. Equilibrium that's when there's no unbalanced potentials driving within the system. Often that means that there's the fundamental property that drives the system is the same or not changing as time goes on. I always love this example. I'm a food engineer by training, so the idea of taking a hunk of meat and dropping it in a bowl of water, basically a brine solution, something has a high salt content, and we let it set, and then it's going to absorb salt molecules as it gets in there. Right? So at some point, you'll reach an equilibrium where the salt entering the meat is equal to the amount of salt leaving the meat going back into the water solution. That's when you reach equilibrium. For us in this course, feel free to pause here so you get these, but these are common types of equilibrium that we will encounter in the Thermodynamics 1 course. Again, pause if you need these, but I'm going to keep moving. Our primary concerns are typically going to be thermal or mechanical, so pressure or temperature. But some of the others, phase does come in up sometimes. We're not so worried about chemical reactions for us here. Okay. 2 definitions here. Process is when a system goes from state 1 to state 2 or from one state to another. So the properties change between states. So a process is something that a system will undergo to change properties. And the path is just simply how it gets from state 1 to state 2 or whatever state to whatever state. Pause if you need this information here, but I'm getting ready to move to the next slide. Oh, actually, there's additional stuff here, right? So if I've got, so my process would be just simply how it would get between these different properties from one state to another. Okay, so again, pause if you need that drawing there, but I'm going to keep moving. So there are special adjectives we can use to describe process path. ISO simply means constant. And so we can use ISO then to refer to different properties staying the same. We'll encounter isothermal sometimes. Isothermal is not where there's no heat transfer. You can have heat transfer but continue to be isothermal. It's a whole nother discussion later on. Isothermal means there's no temperature change, constant temperature. Iso meaning constant, thermal meaning temperature. Isobaric means constant pressure. Isometric means no change in the volume. Okay, pause if you need it, but I'm going to move on. And a cycle is when the process, do I have this diagram? I do have this diagram. So a cycle is when the process goes from its initial state to its final state. Right? And so basically a cycle is just simply a looping process, right? Whenever it goes from state 1 and goes around and ends up over here at state 2, they're at the same point. That's a cycle. All right, I'm going to quit there. It's a good stopping place. Again, I went a little long in this video, but I did stuff that I normally don't get to in class.